we've been covering a bunch of stuff, and I'm not sure that I've really made this clear. And so I want to do what I can to kind of clarify something. And to do so, I also want to prove something that has not kind of been proven to you yet. So I want you to just think of some randomly shaped object. So a potato or an asteroid. And right now, I don't want to consider what the center of mass is doing. I've just marked the center of mass. Something that's off center for this object. And let's say that the object is spinning with a constant angular speed. I want to identify 4 pieces of the object. I'm just going to take 4 chunks that are somewhere distributed around the object and say that this is piece 1, it has mass 1, and this is piece 2, it has mass 2, this is piece 3, it has mass 3, and this is piece 4, it has mass 4. So I have 4 individual pieces of the object. Now, each of those pieces is moving. So each of those pieces has a certain amount of kinetic energy. We're aware that kinetic energy is 1/2 mv squared. So piece number 1 has kinetic energy 1/2 m1 v1 squared. And piece 2 has kinetic energy 1/2 m2 v2 squared. And piece 3 and piece 4 right, each individual piece has its own amount of kinetic energy. And I could break this thing up into way more pieces and talk about each individual piece, but I think 4 will be enough to get the point across. Probably 3 would be enough to get a point across. One of the things that I think we should consider is that each one of these pieces has a different velocity. Even if we assume they all have the same mass, they all have a different velocity because they're all a different distance away from the axis of rotation. If it's rotating about this spot right here, then each piece has a velocity that's based on how far away from that spot they are. So consider that there's a distance r1 that goes from the axis of rotation to piece 1. And that piece 1, because it's a part of a rotating object, must have a velocity that is perpendicular to that radius. That's got to be true for piece 2 as well. That piece 2 is a distance r2 away from the axis of rotation. So it also has a velocity that is perpendicular to that radius. I'd probably say that piece 2 is the one that's going the fastest, right? It's the furthest away. Well, I'm trying to make that perpendicular. I'm not sure I'm doing a good job. That looks perpendicular to me. So this is V2. I think piece 3 is probably the slowest piece because it's the closest. So R3 and V3. And then finally piece 4, a distance R4 away, and it's going to have velocity, somewhere in the middle there, V3, V4. Right, each of these pieces has a separate linear velocity, but we could, because we understand kind of the kinematics here, we could write that their kinetic energy in terms of their rotational velocity. We might want to do that because the whole piece has only one rotational velocity. So if I extend that to each of these pieces, I can begin to get a picture of how much energy the whole object has. You see, although the object is spinning, the individual pieces of the object have the basic building blocks of kinetic energy. They are moving. And all movement is energy. But because they're moving in a way that it connects them all together, we could write the kinetic energy of this object in terms of how fast the object is spinning. So I'm just going to add these things together and extend it to the idea that this could be an infinite number of pieces. Just give myself a little bit of space here. I am going to notice that I have a 1/2 in all the terms. So if we were to get the sum, I'm going to pull out all the 1/2s. I'm also going to notice that all the terms have an omega squared in them. You guys see that too? So I'm going to pull out the omega squared here. What I'm left with inside is m1r1 squared plus m2r2 squared plus m3r3 squared, and so on. First, do you see what all of this must be? Do you see it clearly? This is clearly the sum of mi/ri squared for every piece of the object. This is where moment of inertia is derived. Moment of inertia is derived from kinetic energy. It's where it came from. It is the basics for how we define inertia, because kinetic energy is the basics for how we define energy. Inertia has always played a role in energy. It's always been right here, front and center. It's not as prominent a role as the velocity of the object. The velocity has always been a more overwhelming portion of the of the energy. But moment of inertia is there. It's inside the kinetic energy of a spinning object. So I hope it's clear that rotational kinetic energy would be 1/2 I omega squared, where I is defined as the sum of each piece and the distance squared. Now, another part of this is the consideration that an object can have both rotational and translational velocity. So although these pieces have individual velocities based on their rotational rate, if the whole thing is moving, the whole thing can still have 1/2 big M v squared, where this is the velocity of the center of mass. So objects can be rotating and can have one form of energy, rotational kinetic energy, and objects can be moving through space and have another form of energy, that's their translational kinetic energy. But that would mean the total kinetic energy would be the sum of these two. As stated before, energy is energy. So if an object is rotating and is moving through space at the same time, its total energy has to include both the translational kinetic energy and the rotational kinetic energy. So consider some of the things that we might be talking about here. A football, when it's thrown, it's given both kinds of energy. There's an unbalanced torque against the laces that gets it to spin. That's rotational kinetic energy. But there's also the pressure against the side of the ball, generally friction or your grip, that's giving the ball translational kinetic energy. They're not connected together. How you spin the ball is separate from how you push the ball. But together, that gives the ball two forms of energy. Now, this could be connected together. And the most likely scenario of that would be to consider situations like this. We've had this problem before, and it's one that's should not be particularly out of your focus. But if we have a box at the top of a ramp and there's low or no friction, then we can figure out how fast the box is going at the bottom, either using forces, which is the most obtuse way to do it, or using energy, which would probably be the best way to do it. We remember that the box has potential energy here at the top of the ramp. And if nothing takes that energy away as it slides down the ramp, that energy is converted to kinetic energy at the bottom of the ramp. Right? Simple story from first semester. This if there's still no friction, that's the same story here. Right? If there's still no friction, this object slides down the ramp and converts that potential energy into only 1/2 mv squared. It's important to understand that if there's nothing to cause it to spin, then the energy is still just translational. It still just slides. But if we effectively make the amount of friction non-zero, and there is friction now, then this object will both spin and move down the ramp. Saying that at the top here, it's going to have gravitational potential energy. And then by the time it moves from here to here, it's spinning. So it's got rotational kinetic energy. And the center of mass is moving, so it has translational kinetic energy. I need you to think of every single problem you've done this year where an object's gone through a loop or gone down a ramp or gone down some track. In every single case where the object was sliding, you now need to consider that the problem could involve it rolling. And that changes the nature of the problem. And perhaps in ways that are going to feel a little unpredictable at the beginning. First, objects that roll down a ramp like this, we saw it with the ring and the disc. Do they make it to the bottom at the same time? No, they don't make it to the bottom at the same speed either. An object that's harder to turn is going to require more energy to turn it. That means more of the energy will be diverted to rotational kinetic energy. So the ring, when it gets to the bottom, isn't just last to the bottom, it's also slower when it gets there because it was harder to turn. And it took more of that energy away in the form of kinetic. If it's rolling, it still must be stated at the bottom, V equals omega times R if it's rolling. That will have to be true. Let's play this out so that you have an idea of how this is going to work. Pick your favorite rolling object. I don't care. You got 4 of them. Disc. All right, so this is a disc rolling down because there's lots of rolling discs in the world. So it's a disc. And let's give it the standard properties, right? Mass M, radius R. That all good? Let's say the height here is, well, let's just stick with it. H. All the basics. I want to find an expression for how fast the object is going at the bottom. All right, just do a basic conservation of energy question. So if we start with the object at the top, we know up here it's not rolling at all, so I can get all those things gone. And up here we have all gravitational potential energy. So standard MGH. Makes it to the bottom. Once it reaches the bottom, it's converted that energy into rotational kinetic energy and translational kinetic energy. So at the bottom, we have 1/2 mv squared plus 1/2 I omega squared. Doesn't matter that there was friction acting in the problem. We did the friction problem last week, and I do want to just remind you that in this problem, the same group of forces from last week is still here. That's still something you need to be conscious of, that there's weight acting downwards, there's normal force acting upwards, and can you tell me the direction of the frictional force? Is it up the ramp or down the ramp? It has to be in the direction that causes the object to spin, which means it has to be up the ramp. It has to be the direction of the frictional force. It's got to cause the spin, and it's spinning this way. Just remember that. So those are the forces that are acting on it. When it gets to the bottom, part of the reason it's slower is because it's not just mg sine theta pulling it down the ramp. It's mg sine theta minus friction. that minus friction is diverting the energy. It's doing work. It's a frictional torque that does work to change the kinetic energy of the object. This is the language you're going to have to use. Justify your answer. This is the justification. Friction in this case does work. It changes the rotational kinetic energy of the object. This friction isn't just heat. It's not just leaving heat along the length of the ramp. This friction does legitimate work, changing the kinetic energy of the object. Now, as a problem goes, this all just equals mgh. Just like the old days, we would do this and we'd find V. But now we have two different things for V here. Just like with forces, if this statement is true, if it's rolling, then you have the capacity to potentially put this all in terms of V or all in terms of omega to find out how fast the object's going at the bottom. So let's consider doing that work real quick. Let's put it all in terms of V. I think that's probably the most useful way to do this. So 1/2 mv squared plus 1/2 I v over r squared equals mgh. Now we said this is a disk. I'll give you a choice. Do you want to run this problem in terms of I and put in that later, or do you want to simplify it now and put it in now? I think you'll benefit by putting it in later. So, but it's faster to put it in now. So if it's the AP exam and you know the shape, you put it in now. It's faster. But if it's me teaching and we have a moment, let's put it in later. That way we can put in any shape and see how it affects the answer. So I'm going to get rid of the distractions. We're going to focus just on this for a minute. We're just going to solve this for V. So I'll have 1/2 mv squared plus, I'm going to regroup, 1/2 I over r squared times v squared equals mgh. Now look, as an aside, we know that I is going to be something that rolls, right? mr squared, 1/2 mr squared, 2/3 mr squared, 2/5 mr squared. Do you see in the future when we plug this in, the r squared is going to cancel and all the m's are going to cancel, just like before. So we know that that's the future. And if it was just sliding without friction, we know that this would have equaled the square root of 2gh because we've done it so many times, right? Something slides down a ramp with no friction, that's how fast it's going when it gets to the bottom. So just keep that in mind as we work this out. I'm going to do the obvious, multiply across by 2 and factor out the v squareds. I'm going to solve it for v. It's going to look like yucky, but it'll be okay. You guys are smart kids. You'll survive. We'll take that square root now. Okay, we did all the heavy lifting now. It looks yucky, right? It's terrible. And just look at that, it's a mess. Let's pop in one of the eyes. We'll do the disc first. So let's put the disc in. So v equals the square root of 2mgh over m plus, well, I is 1/2 m r squared divided by r squared. All right, we put it in a disk. I'm noticing right away I can cancel the r squareds. Are you noticing that? So cancel the r squareds and I just get 1/2 m. I'm noticing in the denominator, I have 1m plus 1/2 m. That's 3/2 m. I'll give you guys a second if you're trying to write a logical progression. I don't want you to miss that, but I'm going to cancel the m's now. And I'm going to get rid of my compound fraction by multiplying both top and bottom by 2/3. And get the square root of 4/3 GH. Right? This is the result of a disk. Again, compare it with just sliding down. If it was just sliding down with no friction, square root of 2GH. Rolling down, square root of 4/3 GH. It's slower. We kind of expected that. We diverted some of the energy, and that energy went into spinning the object. Of course, if it was a block and it was sliding, I bet we would have lost some energy too, right? The friction would have taken that energy away. This energy wasn't taken away. This energy is still with the object. That's the difference. When something slides, the friction takes the energy away and the energy's gone. When something rolls, the energy's still there. It might be traveling slower than if it just slid down the ramp, but you maintained the energy. It's just in two forms, translational kinetic and rotational kinetic. But here's the next thing. Let's do that again. But this time for the ring. That's just mr squared divided by r squared. All right, I'm going to branch this off and do the ring. So if I do the ring, the r squared still cancel. I get m plus m. This time, the m's cancel and the 2's cancel. I get v for a ring. It's just going to be a square root of gh. So even slower, right? The ring is slower. It's harder to turn. But I want to drive this point home. So solid sphere, ball, solid. So that's 2/5 mr squared divided by r squared. All the same things happen again, right? The r squareds cancel. I get m plus 2/5 m, which is 7/5 m. The m's cancel, but I get 7/5 there, so I have to multiply top and bottom by 5/7. So I get the square root of 10/7 GH. So this is for a solid sphere. So faster than the disk, right? 10/7 is bigger than 4/3. The point here is to recognize that objects that roll will roll different. They divert the energy differently. There was still a finite amount of energy. And the next thing to really do here is to consider how AP might be interested in the energy of a problem. So we did a bunch of work, but I want to go back to the very beginning right here. We have two versions of the energy. We found that, say, for the disk, the speed ends up being 4/3 GH. That's how fast the disk was rolling when it made it to the bottom. Well, that means some of the energy is here, and some of the energy is here. You could be asked to figure out how much. The total energy is still mgh. That's how much you started with. But a very common thing for like me to ask would be, what percentage of that energy is translational kinetic and what percentage of that energy is rotational? I'm asking legitimately right now, could you do that problem on your own without me helping? Okay, then try it. Right now, find out how much of the kinetic energy is translational kinetic energy. Because whatever isn't translational is rotational. So when it makes it to the bottom, what is the percentage of the energy that is translational kinetic? Let's assume the disk, since that's what I wrote here. For those of you who don't know how to do it, we know the total energy. We want what fraction of it is kinetic. So you're going to make a fraction with mgh in the denominator. And the top is going to have the expression for translational kinetic energy. So if I wanted to find the percentage of energy, I'd put mgh here, because that's 100%, right? That's the amount of energy I have. The translational kinetic is 1/2 m. I don't want to put v here, because I know what v is. V is 4/3 gh squared. Well, not squared, because it's the square root. There, let me put the square root squared. So I put in the value I had for the velocity, because I want something that's in terms of gh, so I get a true fraction. So I square my square root, and I know I don't need to keep going. I know you guys can do this part, but we might as well finish. I see the 2 and the 4. I'll just cancel that out and get 2/3. So this all becomes 2/3 mgh. The mgh clearly cancels. And my answer is 2/3, or 67%. So when the disk rolled to the bottom, 67% of the energy was translational, which means obviously 33% had to be rotational. Now, do you think that split is the same for a ring, or do you think it's different? It's got to be different. The velocity was different. So I want to come back to where we started here. An object that rolls down a ramp is experiencing a group of forces. We talked about the forces last week. The analog between net force and work is still at play here. The difference is that in this problem, gravity did work on the sphere to change the translational kinetic energy of the sphere. Friction did work on the sphere to change the rotational kinetic energy of the sphere. The definition of work stays the same. Net force times distance equals work. The simplified version of work, it's going to stay the same. mg sine theta did work pulling the object down. At the same time, work was done by an unbalanced torque. It's not going to be distance here, it's going to be delta theta. This is work for torque. In fact, let me put that here someplace. If force dot distance equals work for translational forces, then torque dot delta theta equals work for rotational forces. Work's a little different here. And this question about doing work using a torque is seldom, if ever, part of a problem. There's no reason for it to be there. We generally deal with problems where we're rolling and stuff like that, but you could calculate the work this way. But because we don't tend to have things like friction and other things acting, we tend to not do work problems involving torque in this manner. But I do want to remind you about this. This would be meter newtons times radians. This would end up being joules.
Good morning, pardon the interruption. At this